Darren, welcome to the show.
Hi Jamie, thanks for having me.
Myth or fact? Sodium-ion batteries are cheaper than lithium-ion batteries. What do you think? In today's episode, we clarify several claims or myths around sodium-ion batteries, and to do so we have a real expert in the field to help. Darren Tan, the CEO of UNIGRID Battery, joins me for the last episode of 2024. We cover topics around technology, manufacturing and commercial adoption, taking a deep dive into the history, current capabilities and future scope for sodium-ion batteries. We hope you enjoy. Excited to talk about all things sodium-ion today. And this is actually the last episode of the year, last episode of 2024. So as you said earlier, we're saving the best one to last.
Yeah.
So thanks for joining. So let's start with why sodium is your focus. Kind of why have you chosen that as your focus, and why you're so passionate about sodium-ion batteries?
It's a great way to start the podcast. I think it's not so much that sodium is our passion, but rather we want to find ways to achieve our energy transition goals. And me personally, I believe sodium is the way to do it, not the solution to achieve these goals. If we, meaning us humans, we ever want an energy storage infrastructure that is as reliable, as safe, as affordable as, for example, our water infrastructure or food infrastructure. We need the ability to store energy, just like with the way we store water and food. And the way we achieve it has to be through a technology like sodium-ion batteries. In the past, anytime we wanted water, we had to go to the river or dig a well. But today, there's water storage in every building, in every home. So we basically have water on demand, clean, access 24/7. Same for food, because now we have ability to store food anywhere we go. So if we want the same for electricity, access to clean, affordable, safe electricity anytime, we're going to need equivalent electricity storage in as many places as possible, and do it as safely and cheaply. Clearly, this cannot be done with lithium sustainably. Lithium is, after all, a finite resource on Earth. Sodium, on the other hand, is vastly abundant. There's so much sodium in the world, and in the United States alone, there's 90% of the world's sodium reserves. Ironically, we put a lot of sodium in our food here, in our burgers, in our fries. We should put some in our batteries too. That's what we always like to joke about. Yeah, so that's why we pick sodium.
Let's go into the history first before we're going to look into some myths and some facts around sodium-ion, because I think there's some misconception in the market, and we have the perfect expert here to kind of set the record straight. So first of all, kind of give us some history on sodium-ion, kind of what's the current status of the technology and the chemistry, so the capabilities, the current production levels, and where do you see sodium-ion going in the future?
Where to start? So sodium has a long history of development. It's been worked on since before either of us were born. But I won't talk about the ancient history. Let's just focus on the last 10 years, because that's a little bit more recent. So even when sodium was worked on in the last 5 to 10 years, it's clearly not new. They had a good baseline to start off with. But throughout this time, given that the prevailing value proposition of batteries in this period has always been how we can better serve portable devices, and more recently, long-range vehicles, using lithium-ion always made more sense. Right? Sodium haven't came into the spotlight. But today, when most customers and consumers, they want electric cars to be as affordable as combustion cars. We want a safer grid. We want a more reliable storage capabilities. We want to put batteries in indoors. We want higher power batteries to balance peak demand. We want to stop paying peak prices. We want a lot of things, even things like we want sub-zero temperature performance so we can stay warm during winter, which is really appropriate right now. So when we consider all these new emerging trends and consumer expectations, sodium-ion start to make a lot more sense. So these new demands and evolving applications really triggered a lot of sodium activity in the last 10 years. Mainly around legacy cell makers, which are mostly based in Asia. So this includes the likes of large cell makers like CATL, which really started the sodium race, I think somewhere in 2021 during the pandemic, during the peak of lithium raw material prices. So fast forward to today, there's already about gigawatt levels of announced sodium-ion battery production, mainly in China, but starting out in many other places in the world too. We see a lot of deployment of sodium-ion in both electric cars and energy storage at similar scales. In fact, if we think about and compare across all the next generation battery chemistries that have been developed, lithium metal, like this, high silicon, solid state batteries, metal air, molten salt flow batteries, aqueous batteries. If we compare across all this, sodium-ion is indeed one of the fastest growing in terms of technology readiness, in terms of production rates, in terms of adoption rates. And I think that's really exciting to see.
Interesting you mentioned the growth of sodium-ion batteries versus other chemistries and other options. Where do you see the most valid application areas? Do you see that in EVs, energy storage, grid storage? Talk us through the most viable application areas.
I think that's it's difficult to put a blanket statement across which application area because we see different trends regionally. In the West, where there is mostly an open electricity market, there's a lot of incentive to store energy in stationary applications because people want to stop paying. People want lower electricity costs by making use of renewables, and people want to move away from fossil fuels and things like that. But in many parts of Asia, especially Southeast Asia and South Asia, a lot of the electrical grid is nationalized. So there's almost no incentive to store any energy because I'm paying the same price regardless of what time I use the electricity. So there is an uptick in adoption for light vehicles instead. So we're talking about electric two-wheelers, electric three-wheelers. Traditionally, they were powered by diesel engines or lead-acid batteries. And they tried moving to lithium-ion, but in those places, in those tropical regions, the climate can get very hot, which is not ideal for lithium-ion. So there's strong interest of sodium-ion there. So if we notice the common trend among all this, is that none of them were, I would say, predominantly served by lithium-ion before. They were always new applications that were served by that is appealing to be served by sodium-ion rather than replacing existing ones. Yeah, hope that answers the question.
Yeah, that's great. Thank you. And first of all, how long have you been working with sodium-ion batteries, Darren?
Well, the company started in 2021. That was the pandemic. During my PhD, we worked on lithium-ion chemistries. I worked on solid-state battery. I worked on lithium metal. I worked on silicon. So we see a lot of the pains and struggles there. Especially with scaling and production. That's how we can come to the conclusion that sodium-ion can scale much quickly because it can overcome a lot of these traditional challenges. When we started the company in 2021, it was still the pandemic, so we incubated in the university for a year. We moved out in 2022. We started focusing on developing the product, working with early customers. Right now, we are in mass production of sodium-ion cells, modules, and packs, and we'll be expecting to ship large volumes of this to customers next year.
What would you say, to share with our audience, what do you say the biggest lessons that you've learned during your process of developing sodium-ion batteries?
I'd say the biggest lesson is that actually it's also a common misunderstanding that sodium-ion, in our opinion, will never replace lithium-ion. Many expect this to occur. Many ask when sodium-ion will replace lithium-ion, but I believe lithium-ion is here to stay. For the same reason, lithium-ion did not replace alkaline batteries, and alkaline batteries did not replace lead-acid batteries. There is very little precedent for any new battery technology to replace an older one. Instead, it always serves new applications that previous technologies cannot serve. It always enable new things that we cannot imagine today. Right? When I was playing with AA alkaline batteries, I never imagined lithium-ion in a smartphone, like 5 to 10 years later. And when I was using lithium-ion software, I never imagined a different chemistry powering electric vehicles 5 to 10 years later. So today, will we imagine sodium-ion powering a new set of things 5 years from now? So the lesson is we should not try to replace the lithium-ion market, but instead look towards new markets that currently don't exist or that cannot be served by lithium-ion, but will be enabled by sodium-ion instead.
We could probably talk for hours about those other potential options and exciting things that batteries could power. But that's a really good way of looking at it. Well, let's get into the quick fire questions then. So we've got a few different categories. So questions related to technology, questions related to manufacturing, and then commercial adoption, the final one. So let's start with the technology section. So myth or fact, sodium-ion batteries have lower ED than NMC and LFP.
ED mean energy density, right?
Energy density, yeah.
I think for all this question, I'll give you a short reply and then a longer explanation. Because, we want to do it like a real style. So energy density in general, yes, sodium-ion batteries do have lower energy density in general than lithium-ion, both in weight and space. Sodium-ion is both heavier and has a higher deployment footprint than lithium-ion today. However, there's a lot of ongoing innovations in the sodium-ion space that may soon enable energy densities to be comparable with some types of lithium-ion battery, specifically lithium-ion phosphate, one of the most commonly used lithium-ion batteries today. In fact, the current state-of-the-art sodium-ion is already comparable with LFP in terms of watt-hours per kg. It still has about 20% gap to bridge in terms of watt-hours per liter, but I think it can get there in the coming months or years even. Additionally, overall, we're still quite early in the sodium-ion development space. There's still a lot more potential for improvements. In North America, teams are only just starting to work on sodium-ion. We hear about the LANS consortium starting out, led by Argonne National Lab. We hear about multiple other new programs that are coming out. So it's going to be quite exciting to see what innovations will come out in the next few years that allow sodium-ion to exceed lithium-ion in energy density. Some of the interesting approaches are things like enabling anode-free sodium-ion batteries. In fact, I believe if any kind of anode-free battery were to succeed, sodium will succeed first before lithium. This may get a lot of people upset, but this is purely from a fundamental scientific perspective. So sodium-ion has thermodynamics. Anode-free sodium-ion batteries have thermodynamics on its side. Its anode is a lot more interfacially stable to most electrolytes, which is why we see a lot more successful cases of sodium anode-free batteries demonstrated in the literature and sometimes commercially as well. And if that could be achieved, then we will see definitely energy densities exceeding some of this lithium-ion battery.
Next question, myth or fact? You alluded to this earlier, and especially this time of year, it's very important, and consumer demands are ever increasing. So, Nate, sodium-ion batteries can operate at sub-zero temperatures.
Yeah, this is absolute yes, definitely true. We see a lot of claims of sodium-ion operating at way past sub-zero temperatures. In fact, it has been shown to operate at up to negative 40 degrees Celsius, and can possibly go lower as well. At 40 degrees Celsius, negative 40 degrees Celsius, which is about negative 40 Fahrenheit, you can still get a good chunk of your battery capacity, 80% or more, some even 90%. The reason for this is actually another common myth. It's not related to sodium or lithium, but rather the electrolyte. It can do low temperature not because it's a sodium-ion battery, and lithium-ion cannot do not because it's lithium, but because of the fact that lithium-ion requires the use of a specific electrolyte component, which is called EC, or ethylene carbonate. And this material is very viscous at low temperatures. So it doesn't work well below 0 degrees. Hence, if you operate lithium-ion, like a lithium-ion LFP cell, and -20, for example, you get maybe a third or worse of its capacity. Sodium-ion doesn't use this electrolyte component. It uses another that doesn't have this viscosity issue at low temperature. So you can basically avoid this challenge altogether, and you can operate the sodium-ion cell at very low or even very high temperatures as well.
This is great. I'm learning a lot so far. I'm sure our listeners will be too. The third question, so myth or facts, sodium-ion has lower rate capability as it's a bigger ion.
This is a very interesting one because we tend to think that bigger or faster things move slower. That is true, especially for me after Thanksgiving. But it's very different at the atomic scale. In fact, I'd say this is a myth. The answer is no. Sodium-ion in general has a higher rate capability compared to lithium-ion, which is counterintuitive. There are many multifaceted reasons to why this is the case, but I'll just talk about two specific ones that are more common. The first is the anode. Sodium-ion batteries generally use hard carbon anodes. And hard carbon is a type of material that can receive and deliver ions much quicker than graphite. And it doesn't matter what ion. It could be sodium, it could be lithium. Graphite is often the rate limiting factor for most power capabilities in lithium-ion batteries. So when you compare graphite-powered lithium-ion and hard carbon-powered sodium-ion, you can achieve much faster rates for sodium-ion. That being said, if you can build a lithium-ion battery using hard carbon anode, you can also achieve an extremely high power lithium-ion battery. And this actually also applies to the low temperature capability. If you build a hard carbon anode with an LFP cathode, making a high power lithium-ion battery, you can also operate it at -40 degrees Celsius because you can once again avoid that ethylene carbonate component that you have to use whenever graphite is used in the anode. So once again, it's not about sodium and lithium, it's about the specific components of the chemistry. So that's the first reason, the anode. The second reason is the electrolyte. Because the sodium ion is bigger, and the bonds between the sodium ion and the solvent in the dissolved state are much weaker. Which means that it requires less energy to break these bonds. And you need to break the bonds every time you put that ion into an electrode. So because it needs so much less energy, the ions can move in and out of electrodes a lot easier, a lot quicker. And this act of breaking the bonds, often called a desolvation energy, is the common bottleneck for lithium-ion electrode interfaces as well. So these are just two that are commonly reported. There are many other reasons as well, specific to each chemistry. But overall, I'd say the trend is showing that sodium ion has a higher rate capability than lithium ion, and therefore translates into higher power delivery too. So you will see sodium ion being able to give extremely high pulse power. If fast charging is going to be enabled, it will also be enabled by sodium ion first. For vehicles, yeah.
And two more questions left for the technology section. So myth or fact, sodium-ion has a longer cycle life than LFP?
That's an interesting one. So this is often claimed, but it is not yet proven. I'd say it's neither fact nor myth yet. Today, LFP can achieve about maybe 2,000 to 3,000 cycles at 100% depth of discharge. And you can achieve even more at lower depths of discharge. Some have even shown 10,000 cycles of LFP if you, control your operating window to a certain extent. Sodium ion has not yet had enough time to be tested for real cycle numbers to this extent yet. It takes a few years just to get a couple of thousand cycles. So to get even 10,000 cycles, we gotta wait a long time. And that is also assuming that the design doesn't change, that we start today and we just let it go all the way to the end of the decade. In reality, the design will keep changing, so we keep starting the race again and again. So, today the best we can do is use extrapolations. We can use measurements of coulombic efficiency, look at the numbers to extrapolate, and we can judge where we expect the sodium ion to reach if the trend continues. And based on those extrapolations, we can. It has been reported that the cycle life can exceed LFP. But I'm an engineer. I care about real data sets, so I only believe it when I see it happen. So my answer to this is only time will tell.
Another kind of comparison one here, but really interesting what you mentioned before about we shouldn't compare different chemistries like lithium-ion, maybe look for different areas, but this is another comparison one. And I should have mentioned at the beginning, these myth or facts, we took a lot of questions from our community. A lot of people wrote in for this episode. There's been a lot of interest around sodium-ion batteries, and what we did was we categorized them from technology, manufacturing, and commercial adoption. So the final one for technology is sodium-ion is safer than lithium-ion. Myth or fact?
Yeah, that's another common one too. I have to unfortunately provide an unsatisfying answer that this is also not proven yet. There has not been conclusive evidence to say absolutely that commercial sodium ion is safer than lithium ion. It also not proven that it is not safer than lithium ion. In the last 1 to 2 months, very recently, a number of third-party independent studies have reported test results that show that lead oxide-based sodium ion, which is the most commonly used sodium ion today, especially coming out of China, has similar, if not slightly worse, safety properties compared to lithium-ion NMC. And I think you can share. I will share with you those links that you can put in the chat. One is done by U.S. Naval Laboratories, another is done by Sandia National Laboratory. It's a really interesting report because they obtained a number of commercial sodium-ion batteries and tested them using the same metric, which is ARC testing, accelerated rate calorimetry testing. So that was kind of surprising and shocking to the community because we've heard a 1 year of media reports saying sodium-ion battery is safer. And then the independent studies show that, hey, come on, it's not true. But I also need to highlight that it's for one specific chemistry of sodium-ion, which is the lead oxide base, similar to the NMC lead oxide. So if you think about it, it's not that surprising that the safety properties are comparable. Testing is also ongoing for other types of cell chemistries, like polyanion cathodes, Persian blue cathodes, many all these common chemical groups as well. Early results indicate that those types of materials are safer and much safer than lithium ion. But it is also very difficult to compare these on an equal basis because many of these chemistries have much lower energy densities compared to lithium ion. And much lower compared to the lead oxide counterparts. So when you have a battery with much lower energy density, you also expect it to release less energy, right? Hence, it's difficult to conclude whether it's safe until it is done on a very big system. But overall, I mean, there are promising signs that it could be safer. I think the current confusion and frustration stems from the fact that there is a lack of universal standard or definition of what safe means. When we compare energy density, power capability, weight, space, whatever, there's always a number, 1 hour per kg or whatever metric that is used. But there's no such metric for safety. Can we say that this battery is a safety of 47 or 35? There's no way to do this. So that creates a lot of confusion. So we need, as an industry, as a community, we need to come up with some kind of standards to use. Today, the best we can use is what UL sets, which is the standard used for energy storage systems, which is the 9548 test. That typically is based on the ARC test, which is what the third-party institutions have done. And I think that's a good place to start. At the end of the day, I think like lithium ion, we will expect a range of safety properties. Today, we roughly know the safety differences between NMC, LFP, LTO, for example. right? It is likely that sodium-ion will have a range of safety chemistries as well. You will have a certain type that is a little bit more unsafe, but perhaps higher energy. You have a certain type that is more safe, but low energy density, and maybe different types with different properties. So I think it's up to us to develop the best compromise possible.
Yeah, it's a really good point. These are difficult questions because, as you say, one's safer than the other. It's hard to measure, and yeah, we probably need a better system to be able to define that. But we move on to manufacturing. So some manufacturing-based questions. So, myth or fact: sodium-ion can be made on lithium-ion manufacturing lines.
This is a very clear yes. Sodium-ion can definitely be manufactured and scaled using the exact same manufacturing infrastructure that was built for lithium-ion. I know this for sure because we are doing exactly that right now. We are currently producing about megawatt-hour scale of sodium-ion products without the need to build anything new. We make use of the current overcapacity around the world. There's a lot of underutilized lithium-ion factories around, and that is a blessing not just for us, but all the sodium-ion developers out there. We make full use of it. Of course, there are some differences, minor ones, not related to machinery or capital investments. The material powders that go into the factories are, of course, different. One is lithium-based, one is sodium-based. Your electrolytes are different. You may have to adjust your dry room dew points slightly to account for different chemistries. Some materials are more moisture sensitive than others. But overall, there is a literal drop in manufacturing capability of sodium-ion on lithium-ion manufacturing lines.
Interesting. And the next question, you kind of alluded to a little bit of that in the answer. But the question is, sodium-ion uses the same material supply chain as lithium-ion. Myth or fact?
I'd say this is mostly yes. It's not as strong of a yes as the previous question. Most of the inactive materials used in sodium-ion are also used in lithium-ion. Things like your current collectors, your binders, your additives, and even some of your electrolyte components as well. The main difference, as I alluded earlier, was the active materials, and like your anodes and cathodes and things like that. And this needs time to build a mature supply chain for. The good news is that just like the cell manufacturing, the sodium-ion active material manufacturing are also made in the same lithium-ion material factories. They are also sintering based type materials. They're also combustion type based materials. So it could scale as quickly, but the main barrier now is that we cannot yet decide which material to scale. The sodium-ion active material development space is kind of like the Wild West currently. It's like where lithium-ion was 20, 30 years ago. There's so many different cathodes to choose from. No one knows which is going to be the winner. And it takes time to funnel that down into your NMC, LFP, LCO, or LTO. So sodium-ion will undergo the same transformation too. We have our beliefs and bet on which are the final ones are going to be. We could be wrong, but we place our bets right now so that we can pick one to scale.
And this one's kind of manufacturing, kind of logistics. Myth or fact: sodium-ion can be shipped at 0 voltage or 0% capacity.
This has been an attractive point for a lot of logistics and OEMs as well. Because let me answer the question first. The answer is yes. Actually, currently we ship all our products at 0% SOC. So our customers or adopters can leave it or store it at 0% for as long as they like, basically, on the warehouse. And the ability to do so dramatically reduce the risk of fire, reduce their insurance requirements. The local fire departments, are less fearful that something will happen, because if everything is at 0%, there's not that much energy to release. And likewise, this will also help logistics companies when you're shipping vast volumes of batteries. When you store them long term without thermal management in the warehouse, that really reduces risk. So The ability to do so, it, it helps the whole supply chain. Now, why can sodium-ion do 0 volt or 0%? It's once again not related to sodium or lithium, but rather the current collector, which was surprising when I first learned about it too. It is specifically the copper current collector. So copper is the typical current collector used in lithium-ion batteries, and sodium-ion doesn't use copper. It uses aluminum foil on both sides of the battery. In lithium-ion batteries, copper in the current collector typically dissolves into the electrolyte. Some of it dissolves into the electrolyte, which isn't a bad thing. But what happens is when the lithium-ion battery is discharged below a certain voltage, this dissolved copper starts to deposit on the electrode and starts to poison it, causing cell degradation. And how much it degrades, how fast it degrades, depends on how often the battery goes below the 0 voltage, how long it stays at the 0 voltage, and basically how poorly you treat your battery, right? Which is why we should try to not let our phone batteries go to 0% too often. Try to keep it, leave some charge in there, right? And if we do that too often, sometimes, we have an old phone, we put it in a drawer, we forget about it for a year, we come back, it cannot turn on anymore, or it turns on but it dies really quickly. It's because of this reason. So this is the reason why lithium-ion needs to always be kept at some degree of charge. Typically based on UN 38.3 shipping regulations, it is shipped always at 30% SOC. But sodium-ion doesn't need to be at this requirement. So although the same regulations stipulate that sodium-ion should be shipped at no more than 30%, we still ship it at 0% anyway, because there's just no benefit of shipping it at higher state of charge. Yeah. So hope this answered the question.
Yeah, really interesting. And then an interesting point about phone batteries not letting it run down to zero, something that my wife does all of the time. And it makes me feel very anxious because I'm someone who always has at least 50% on there. It's
Yeah. And you will find that you can use your phone for maybe a year or two longer than your wife.
I'm gonna time it. I'm gonna see. She's got a newer phone than me, so I'm gonna see how the battery life lasts.
But the newer phones are probably designed to die a lot quicker, so you have to compare on the same phone.
True, and of course the AI and things like that, all makes a difference. Fourth question on this section: so sodium materials are easier to process than lithium materials. Difficult question. Myth or fact?
I think it's difficult to define. So when we say sodium materials, I'm assuming we're talking about raw materials, or rather the baseline source of the raw materials, which is the carbonate, right? In sodium is sodium carbonate or soda ash. In lithium is lithium carbonate, because that's what battery manufacturers use to make the active materials and everything downstream from there. Sodium carbonate exists naturally. It is in the rocks, in the salt, and there's a lot of it in Wyoming. So miners and refiners need not go through as complicated of an extraction and chemical treatment process that lithium undergoes. So if we read about how lithium is mined and extracted, it's a fairly high carbon footprint process. Can be pollutive as well, uses a lot of water. But mining soda ash can basically bypass a lot of this. There's also a lot of benefits from sodium materials too, because there is already an established gigantic soda ash industry. There are literal mountains of soda ash lying around for us to use in batteries. Whereas in lithium, we need to do a lot more work. That we need to invest more in infrastructure, in localization of supply chain, and moving it around the world, sometimes from very difficult to access places too. So from these standpoints, sodium materials are easier to process than lithium. But once you get them to the battery grade precursors, then it's basically not very different anymore.
And this last question is super difficult on this section, so good luck answering. So myth or fact, sodium ion is more environmentally friendly? Super broad.
Oh, I hate this question. Yeah, it's really difficult to answer, as you mentioned. I mean, there's a lot of LCA, life cycle analysis studies out there. And they all say different things depending on who funds the project. But I want to focus on one aspect, which is PFAS, or rather the fluorine, dealing with fluorine. Fluorine is probably the last toxic material to resolve in batteries. Because lithium ion, you can move away from cobalt, you can probably move away from nickel, you can move away from a lot of other nasty things, but it's very difficult to move away from fluorine. But if you can remove fluorine somehow, you make it way more environmentally friendly. It's easier to recycle. It's easier to treat for disposal. Unfortunately, very hard to avoid fluorine in lithium ion. There's a lot of benefits, electrochemical and performance benefits of using fluorine-containing components. For example, your salt is fluorine-based. Use PF6 salt. A lot of lithium-ion batteries use FEC additives. Many use fluorinated solvents, other fluorinated additives, precisely because the SEI that contains LIF has been reported to help battery performance significantly. So I think fluorine will likely stay in lithium ion. However, this doesn't apply in sodium ion. In fact, the effect of adding fluorine has been found to be detrimental to sodium ion battery performance, precisely because the sodium fluoride it has a completely different property to lithium fluoride. In fact, sodium fluoride is a complete insulator, so it doesn't help the battery at all. So here we have a chance on a new technology platform to eliminate fluorine directly from the electrolytes in sodium ion. And there are a number of companies working on that already. They develop entirely fluorine-free chemistries from electrolytes, and we're looking forward to using these in the upcoming production scale. Today, sodium ion electrolytes still use NaPF6 simply because it's produced by the same electrolyte folks that produce lithium ion electrolytes. But I think there is a good chance that we can switch to a fluorine-free version quite soon.
And we're on to the last section now from the questions from our community, and this time we've categorized it into commercial adoption. So the first two questions kind of contradict what you were talking about before regarding, it's not about replacing, it's more about looking at other areas. So the first question is, myth or fact, sodium ion will replace lithium ion in the future? I think I know what your answer will be.
Yeah, I think we accidentally answered that earlier already, so we probably jump to the next one.
So myth or fact, sodium ion is cheaper than lithium ion?
This is a no, not today. Sodium ion today is still more expensive than lithium ion. So if you go to lithium ion cell makers and you ask for a quote for, let's say, gigawatt hour scale, you would see numbers that Bloomberg has reported, which is the $50 or the $60 per kilowatt hour, or even less at times. The cheapest sodium ion quotes you see out there are still in the $60 to $80, some even $100 per kilowatt hour range. It's not to say that it will always be the case. This is simply because sodium ion volumes are only a tiny, tiny fraction of where lithium ion production is. But I predict that sodium ion will reach equivalent production rates at less than half the time it took lithium ion to get to where it is today. And when that happens, we will see sodium ion costs falling significantly below lithium ion. The reason is very simple. It's pure logic. If both lithium and sodium ion use the same production factory, use the same production methods, the same number of labor personnel, same degree of automation, then the cost difference now boils down to bill of materials. Right? So if the raw material of sodium is already 100 times cheaper than lithium, despite how much lithium ion prices, lithium raw materials have come down, the baseline cost for lithium carbonate is 100 times less than lithium carbonate. So if my process is the same, my input is vastly different, I can expect my output to track in a similar direction. What this final number and percentage will be, I cannot say for now, but we're still quite sure that sodium ion will be cheaper than lithium ion, perhaps before the end of this decade.
Just 3 more questions from the community, Darren, and then we can let you go. Well, actually, there's one more question from a former guest, and then you can go. But you touched on this before, but I don't think you answered it, so I will ask this question. Myth or fact, sodium ion primarily targets ESS rather than EVs?
Short answer is yes in some places, no in other places. In North America, ESS is the primary target market for sodium ion, no doubt. As I mentioned earlier, it's because of our open electricity market system. There's a lot of strong incentives to store energy. In California, where we are at, the peak prices versus off-peak prices of electricity can be 5 to 10 times in gap. So, the payback times for using battery storage is just so lucrative. So there's strong incentive to do so here. But in Asia, as I mentioned, electricity utility is often nationalized. So there's no incentive to do arbitrage. So although there's still ESS markets there, many of them serve remote areas or certain industrial peak power just to relieve load on the grid, or they serve simply as backup power in disaster-prone regions. So that's why we see a lot of ESS demand in Western economies. For electric vehicles wise, it's a different dynamic once again. In North America, I think we like big cars. We are okay if it's expensive as long as it's luxurious. That's why the mean sale price of vehicle last year was 50 something thousand US dollars. So most people still want this long range. They want a spacious vehicle, and they're willing to pay for it. Because of this, lithium ion works very well. And, there's still limited incentive to use sodium ion, as long as this trend continues. But if we see more pressures or lower cost vehicles, something similar to combustion vehicles, then there could be a case made for sodium ion. But we'll see where that happens. In Asia, most drivers drive within cities. We don't drive interstate as much as we do here. And in these cities, we like small, affordable vehicles, including 2- and 3-wheelers, e-bikes, e-scooters, rickshaws, utility vehicles. And these are extremely suited for sodium ion. So we're seeing a lot of demand for sodium ion for these specific applications. I think whether ESS or EVs really depends. It region specific.
Is that mainly because of the energy density element?
Yeah, because in different markets, there's different drive range expectations or drive distance expectations. If you're almost always only driving in the city, and if you have to go out of the city, you'll take the high-speed train instead, then you probably don't need a 600-mile range vehicle. A 100-mile or 200-mile range vehicle that you can fast charge, it will probably be more attractive.
I didn't know that about kind of sodium ion being more suited to kind of small electric vehicles.
Yes, there's a lot of different aspects to that, and I'm not sure how much time we have to talk about it too. One thing that we may not realize is that many of these small vehicles don't have thermal management too. When you think about motorcycle or scooter, you don't run cooling fluids through the battery pack. That is not as heavily engineered as a passenger vehicle. So any battery technology used in those kind of devices has to be a lot more robust to warm and possibly cold climates, to harsher charge conditions, because many of these application areas also don't have, for example, a Tesla supercharger infrastructure. Many charge at home with makeshift electronics. So the batteries have to take a beating. So a lot of sodium ion batteries can take that beating. That's what makes it attractive.
Well, the next myth or fact to clarify. So sodium ion can serve long duration markets.
I'd say today no, but eventually yes. This is another myth within a myth. Long or short duration technologies are actually the same thing. It only depends on the cost, or more specifically, the levelized cost. If lithium-ion batteries cost $5 per kilowatt hour, it can be used for a long duration, and it can be used for any duration you like. Because the longer the duration, the less frequent you can use it, and therefore the less returns you can get on your investment. So your initial cost needs to be lower. So today, sodium ion is competitive in a similar duration as lithium ion in the, let's say, 1 to 8 hour duration markets. And those are indeed lucrative markets. But with time, as costs come down, not just cell level costs, but system level costs, and if the system level cost can fall significantly below lithium ion, it will start to become very competitive in long duration markets. We mustn't underestimate the system level savings of sodium ion. We are so caught up with the cell level costs, and we forget potential savings at the system level too. For ESS applications, we learned that a lot of cost comes in system integration when you need to, for example, run an air conditioning unit to keep the lithium-ion batteries at the same temperature the entire year. That's fairly expensive to not only build, but to maintain, because air conditioners fail all the time. When you have to include a lot of things like structural bracing, safety, margins, fire suppression systems, all this add to your system level cost. So if you can develop new chemistries that are a lot more robust, can operate a wider temperature range, that is potentially much safer, there's a lot of system level savings that are not often captured in models like this. But I think it could become a reality and accelerate its eligibility for long duration markets.
And a final question from the community. Myth or fact, sodium ion is not yet commercially adopted?
I think that's today say mild no, but very soon a resounding no. Sodium ion is rapidly adopted commercially in Asia right now. We see a lot of it in China, in Southeast Asia, and in India. These are regions that generally have fewer red tape and regulatory requirements to adopt anything. And most customers don't care what the chemistry is. As long as it works, it solves their pain point, they are willing to use it. And sodium ion solves a lot of this. When there's fewer barriers to adoption, and it's available without overcoming a lot of tariffs and a lot of certification requirements, I think it's natural that people will use it. But I think it's also a matter of time before it hits North America and many parts in the West. There are a lot of stricter rules here for good reason. And there are a lot of certification requirements before this can be used here. But although we see slow adoption rates now, I think we expect a sudden exponential increase the moment it happens. And I think this incident will occur before the end of this decade. And many other cases and many other past technologies have seen similar rise as well. Solar is one. We just got to be prepared for it.
Well, this has been great, Darren. I've learned an awful lot today on sodium-ion batteries. A lot of things that kind of thought I knew have kind of been corrected, and I'm sure our audience will have taken a lot from this. So it's almost like a lecture, kind of going through all these elements. So thank you.
I must say too, what I've shared today is the knowledge we have right now. This could change over time as well as we learn new information. If you ask, if we do this interview 2 years ago, many of the things I would have gotten wrong as well. So it's a very dynamic and exciting time now, and I think some of this myths or facts may swap position in the coming years, and we'll see what happens.
I think things are moving so quickly. So as you say, kind of research in a couple of years might look very different. Look forward to that second episode in a couple of years and see where we are. Well, thank you, Darren. The last episode of the year, and good luck for next year. Hopefully for you, the business continues to thrive, and in the meantime, enjoy a nice break.